Welcome to today's deep dive. I'm your host, and joining me to unpack all of this is our resident expert. Let's just jump right in.
Sounds good. I'm really excited for this one.
So I want you to picture a scenario. You are the CEO of this massive engineering firm. You're burning through your budget trying to solve some absolute nightmares of logistics.
Right, like how to route millions of packages efficiently.
Exactly, or how to filter microplastics out of water, or how to design a wing that just doesn't drag. You are stressed.
Yeah.
And then someone tells you there is a rival firm down the street that has already solved every single one of these problems.
And not only did they solve them, but their product testing phase lasted 3.8 billion years.
3.8 billion years. I mean, that is a heck of a head start.
It really is.
And according to biologist Janine M. Benyus, that is exactly what Earth has been doing. She calls it the ultimate research and development lab.
It's a really compelling frame. Her argument is basically that failures are fossils.
Failures are fossils. I love that phrasing.
Right. If something didn't work, if a design was inefficient or energy heavy or fragile, it died out. So what surrounds us today is the survival strategy that actually won.
Which brings us to our topic today. We are looking at biomimicry. But, and I really want to be clear here, we aren't just talking about making things look like nature.
No, not at all.
We aren't just talking about, slapping a beak shape onto a bullet train.
Right, we're going way deeper than the hardware. We're looking at the software. We're diving into how the chaotic, messy, beautiful systems of nature are actually the basis for the star algorithms of artificial intelligence.
Nature and code. Our mission today is to understand how engineers are copying nature's homework, from ant colonies to neuron spikes, to solve these complex computational problems like optimization and adaptation.
We want to understand that translation layer. How do you go from watching a bird flock turn in the sky to writing a line of Python that manages a power grid?
Before we get into the matrix of it all, though, let's just quickly ground this in the physical world.
Yeah.
Just to establish a baseline for you all listening, I think most people know the classic hits of biomimicry, right?
Sure. I mean, aviation's the big one. We wouldn't have airplane wings without birds or self-cleaning paint. That actually comes from studying the microscopic bumps on lotus leaves that repel water and dirt.
And my personal favorite, just because it's so incredibly mundane, is Velcro.
Oh, yeah. The dog story.
Yeah. George de Mestral takes his dog for a walk. The dog gets covered in burrs. And instead of just brushing them off and being annoyed, he puts one under a microscope.
And he sees the tiny hooks.
Catching the loops of fur. Exactly. And boom, he creates a billion-dollar industry.
But he didn't invent the mechanism, did he? He translated it. And that is the key word here, translation. Because now we are moving from physical hooks and wings to the invisible world of software and code.
Okay, so let's define our terms a bit. When we say nature is algorithmic, what does that actually mean? Because a tree obviously doesn't have a CPU.
No, it doesn't, but it has rules. An algorithm at its core is just a repeatable step-by-step procedure for solving a problem. And nature faces the ultimate problem, which is optimization.
Optimization, that's a word that gets thrown around constantly in tech. Give us a specific definition for how we're using it here.
Think of it like a landscape. Imagine a 3D map with thousands of hills and valleys. Your goal is to find the absolute highest peak, the global optimum. In computing, that peak might represent the most efficient delivery route or the perfect shape for a propeller.
But the map is in the dark. You can't just look down and see the whole thing at once.
Exactly. You have to search for it. And nature has been running search algorithms for eons. How do you find the most food with the least energy? How do you find a mate before a predator finds you?
Right.
The solutions nature came up with are now what we call heuristics, basically shortcuts to finding good solutions when a problem is just too complex to solve with brute force math.
So let's look at the first master of this, the ant.
Ant colony optimization, or ACO. This is a massive staple in computer science.
Now, I know the basic premise here. Ants leave a pheromone trail. Other ants follow it. Simple enough. But I've always wondered, if every ant just follows the strongest trail, wouldn't they all just end up in a straight line doing the exact same thing? How do they ever discover anything new?
That is the crucial question. If they only followed the crowd, that would be a completely rigid system. It would fail the moment a rock fell across the path. The magic of the algorithm and the insect itself lies in two things: probability and evaporation.
Evaporation.
Yes. Pheromones don't last forever. They evaporate over time. This is a critical variable in the code. If a path is long, the ant takes more time to travel it.
So by the time it comes back, the scent has faded significantly.
Exactly. But if a path is short, the ant makes the trip fast. reinforcing the scent before it disappears.
Oh, I see. So the short path gets a compound interest effect. The scent builds up way faster than it fades.
Precisely.
Yeah.
It's a positive feedback loop. But here is the probability part. The ants don't follow the trail 100% of the time. There is a stochastic element, randomness. Occasionally an ant will just ignore the strong trail and wander off,
The rebel ant?
the explorer ant. And in the algorithm, this is essential. You need a variable that forces the program to explore new areas of the data map. Otherwise, you get stuck in what we call a local optimum.
Which is like a small hill that looks like the peak, but isn't.
Exactly. You think you found the best solution, but there's a mountain just a mile away hidden in the dark.
Okay, so we have this logic. Reinforce success, but keep a little randomness for discovery. Where are we actually using this? Is this just for routing delivery trucks?
It is used there, but the stakes can be much, much higher. There was a fascinating study from Kashan University in Iran. They applied ant colony optimization to medical diagnosis.
Wow, from picnic crumbs to patient charts.
They were training an AI model to predict whether a breast tumor was benign or malignant. Now, in medical data, you have hundreds of features: age, tumor size, cell density, texture. It's a massive, noisy data set.
It's that dark landscape we talked about.
Right. So they treated the features like the terrain. The ants, which are the software agents, wandered through this data looking for the combination of features that best predicted the cancer outcome.
So the food they were looking for was an accurate diagnosis.
Exactly. The software agents that found predictive patterns laid down a mathematical pheromone. Over thousands of iterations, the system converged on the most efficient path to an accurate diagnosis.
And it worked.
Exceptionally well. It outperformed standard methods because, like real ants, the algorithm is robust. If one data point is noisy or wrong, the swarm corrects for it.
That is wild. It creates this distributed intelligence. No single ant knows the answer, but the colony as a whole does.
That's the main theme here: decentralized control. Which brings us to our next creature. Ants work on the ground, leaving physical trails. But what happens when you are in the air?
Birds, flocks of birds, murmuration.
Or schools of fish. The behavior is very similar. This gave rise to particle swarm optimization, or PSO.
Particle swarm optimization. That sounds a bit more sci-fi than ant colonies.
It was developed in 1995 by Russell C. Eberhardt, an electrical engineer, and James Kennedy, a social psychologist. And that pairing is really important.
An engineer and a psychologist.
Yeah, because they weren't trying to build a math solver initially. They were actually trying to simulate social behavior.
They wanted to see how information moves through a group.
Right. But they realized pretty quickly that the way a flock moves is a powerful search engine in itself. Imagine you're a bird. You want to find the center of a cornfield where all the food is. You can't see it from where you are, but you can see your neighbors.
So what are the rules guiding them?
There are usually three simple vectors, basically mathematical arrows guiding each particle or bird. One is separation, don't crash into your neighbor. Two is alignment, head in the general direction of the group.
Makes sense. And the third?
Cohesion, steer toward the average position of your neighbors. But in the algorithm, they add a memory component. Each particle remembers the best location it has personally found. That's its personal best. But it also knows the best location anyone in the swarm has found, the global best.
So there's a tension there. It's like, I want to go where I remember the food was, but I also see that Bob over there is eating like a king, so I should probably head toward Bob.
Exactly. The particle's velocity is calculated by combining those two poles. This algorithm disperses numerical solutions to explore different areas simultaneously to find a target quickly, rather than searching one by one.
So the swarm can spread out to explore the whole map, but once someone finds a deep valley or a high peak, the whole swarm swoops in to investigate.
That's the beauty of it. It prevents stagnation. It solves that local optimum problem we talked about with the ants.
Yeah.
If you get stuck on a small hill, but the rest of the swarm is gathering on a mountain 5 miles away, you're going to get pulled off your hill.
This is used heavily in engineering, right?
Absolutely. Tuning antennas, optimizing power systems. Anywhere you have a complex system with just too many variables to check individually, you send in the swarm.
It's interesting that both of these, the ants and the birds, rely on a complete lack of central leadership. There is no general ant or king bird telling everyone what to do.
It's entirely bottom-up intelligence. But there is another form of nature-inspired code that is perhaps even more fundamental. It mimics the building blocks of life itself.
Evolution.
Survival of the fittest. In computing, we call these evolutionary algorithms. or specifically, differential evolution.
I love this concept because it sounds so harsh. We're basically breeding computer programs and killing off the weak ones.
That is literally what happens in the code. You start with a population of random solutions. Let's say you're trying to design the perfect aerodynamic shape for a car. You generate 100 random weird shapes.
Most of which will be absolutely terrible.
Most will be literal bricks, but a few might be slightly better than bricks. You run them through a fitness function that represents the environment. It tests them. Then you take the winners and you breed them.
Breeding in math terms means what exactly? Mimicking sexual reproduction.
Exactly. It's called crossover. You take the numerical parameters of parent A and parent B and mix them to create a child. But, and this is the crucial part for differential evolution, you also introduce a mutation mechanism.
This goes back to the random explorer ant, right? To keep things from getting stuck.
Yes, but the mechanism here is fascinating. In differential evolution, you take 3 distinct individuals from the population. You subtract 2 of them to get the difference between them, weigh that difference, and add it to the third. This creates a new mutant vector.
Okay, that's getting a little into the weeds of the math, but why does that specific method of subtracting individuals matter?
Because it allows the mutation to self-adapt. If the population is spread out all over the map, the difference between individuals is large, so the mutation jumps are huge. You are exploring big new territories.
But as they all start to converge on the best solution.
They get closer together, the mathematical difference becomes tiny, so the mutation jumps become microscopic. The algorithm naturally switches from exploring the world to fine-tuning the details without anyone explicitly programming it to do that.
That is brilliant. So early on, it's taking massive leaps across the map, but by the end, it's just polishing the chrome.
Exactly. And this was designed to overcome limitations in classical genetic algorithms. Specifically, it makes it much easier to work with real numbers, continuous data like temperature or pressure, rather than just binary ones and zeros. It's hugely popular now in data analysis and machine learning.
Speaking of machine learning, we really can't talk about biological computing without mentioning the elephant in the server room, neural networks.
Of course.
We see ChatGPT, we see all these large language models everywhere now. But I think people forget that the neural network is literal.
It is. It's a direct mathematical model based on the functioning of neurons and brain networks. Our brain works by synaptic weights. When you learn a skill, the connection between specific neurons strengthens. It becomes easier for the signal to fire across that gap.
Neurons that fire together wire together.
That's the Hebbian theory. Artificial neural networks do the exact same thing. They adjust the mathematical weights between nodes based on training data. They classify, they recognize patterns, they infer predictions. It is essentially using the organizational principles of the human mind to build AI.
Now I'm getting pretty hyped up here. It feels like we have the keys to the kingdom. We just copy nature and we solve everything. But I know you read an article for this deep dive that suggests we might need to pump the brakes just a little bit.
A little bit, yes. We need to be careful about the difference between a useful math model and a catchy metaphor. There's a really interesting critique from the SCI2S group at the University of Granada. They published a paper titled The Paradox of Success in Evolutionary and Bio-Inspired Optimization.
The paradox of success. What is their main critique of the field?
Their concern is a lack of methodological rigor. The researchers warn that there's a flood of new algorithms being published that are essentially just standard mathematical searches dressed up in animal costumes.
Well, someone writes a search algorithm and just calls it the gray wolf optimizer or the cuckoo search to get it published.
Exactly. Many proposals are justified simply by their biological metaphor, rather than real experimental evidence. The critique asks, does the cuckoo search actually offer a new mathematical mechanism? Or did you just take a standard genetic algorithm, change a few variables, and write a cool backstory about birds laying eggs in other nests?
It's marketing over math.
In some cases, yes. It creates unnecessary repetition in the field. They argue that many of these nature-inspired algorithms don't actually perform better than the classic ones we've had for decades. The metaphor becomes a mask for redundancy.
So the takeaway for you listening is nature is a great inspiration, but don't just assume an algorithm is good just because it sounds like something cool from a wildlife documentary. Show me the math.
Rigor is required. We have to test these things against the best existing baselines. But, and this is an important context, the University of Granada group isn't saying biomimicry is bad. They are saying we need to stop reinventing the wheel and focus on the true innovations.
So where does this leave us at the end of the day? We have ants diagnosing cancer, swarms managing power grids, and digital evolution designing cars. why should we care about all this translation layer stuff?
I think it shifts our entire perspective on technology. Translating biological patterns into math allows us to capture intrinsic knowledge of the world.
Intrinsic knowledge. I like that.
Nature has dealt with uncertainty, limited resources, and hostile environments for billions of years. By translating that into math, we aren't just building faster computers, we are building systems that can survive and adapt.
And the real-world impact is huge. The sources mention some high-stakes applications where this is already being used. Assisted medical diagnosis, which we touched on. Intelligent management of transport networks.
And early detection of cyber attacks. Think of an immune system for a digital network. Instead of looking for a specific virus file, you look for non-self behavior, an anomaly in the pattern. That is pure biology applied to IT.
They're also using it for monitoring ecosystems to predict extreme weather phenomena, which is basically using nature's code to save nature.
It really comes full circle.
I want to end with a provocative thought from Janine M. Benyus. She said something that really stuck with me. She said, conscious emulation of nature isn't just a tech trick. It is a survival strategy for the human race.
That really is the big picture. 3.8 billion years of R&D. By copying what has endured for that long, we might just secure a sustainable future for ourselves.
I love that. If we want to stick around, we should probably stop trying to beat nature and start copying the answers she has already graded. So next time you are stuck on a problem, whether you are debugging code or just trying to navigate a crowded grocery store, maybe look at how the ants move. Look at the birds.
They figured it out a long time ago.
Thanks for joining us on this deep dive. Catch you next time.